The course objective of course is that course deals with basic theory of analog. Already second year analog circuit course must have been done, so nothing great will happen from there, basic things can't change. However, from there how do you design a chip, that is the course is trying to. But unfortunately the word design itself says that it has to be, it is not available, that is why you have to design. That means you do not know the specification a priori. So when you are given a spec, how to meet those specs will require a lot of understanding of devices as well as circuits, because then only you can actually meet those difficult specs. And therefore design requires some understanding of basics of both devices as well as circuit, devices to a smaller extent but circuit to a greater extent. So this course will try to give some idea of good design principles and to simplify the design process itself. Okay. This is course content available in the site itself. However, there are some A to D and D to A, some parts were written because that was old course design in which there was mixed signal circuit was part of this course. But now a new course is running mixed signal itself. So we have removed that part. So we have little more time to do earlier things better. Okay. So basically we will talk about MOS models, why analog models are different from digital models, or how bad or how good they are. We will look into SPICE models. So all of you should be aware of SPICE. I will not teach my. So we will talk about gain stages both with NMOS and CMOS. We will talk about cascade, and the word cascode, as the word goes there, will show you. We will talk about basically references, voltage and current. We will talk about differential amplifier, which is our bread and butter, and we will talk based on that op-amp design. We will look into frequency synthesized, VCO based or PLLs. We will look into little bit this year on interconnects, because this is becoming a very tough situation in 2010 or 11 ahead. We will look into some testing, layout issues, and also show you in the current context this word low power, or actually the low voltage low power is written specifically because the misconception amongst designers is that low power circuits are more interesting. It is not, actually it is the low energy. The worry is on energy, not so much on power. Okay. Power into time is energy. So energy is what is worrying us. The battery stores certain amount of energy, it does not store power. Okay. So how fast that will consume. Okay. So we look into it at the end, what is this low power business. The books which I use are not the only books which you should see, hopefully yes, but I like this Razavi's book by Basic Analog Integrated Circuits. Most of my basic part will be actually taken from Razavi's book, okay, which is a very standard all over the world. I have edition 1, but I think now there may be edition 6, 4, 5, whatever it is, by the latest one. Then there is, this book gives, as I say, mostly on the analysis part very strongly. Then we will talk about something which is more practical, which is a book written by Baker Lee Boyce. He is one of the pioneer researchers in the area of analog. We will also look into a very old book, old in the sense it was available in my time, so old that. Of course edition has changed, the authors, Professor Gray is still Paul Gray is still there, but the other Mayer, Hurst, Lewis, this keeps on changing. Mayer of course is older one, but I think these new ones which Hurst and Lewis have joined. This is one of the oldest book on analog integrated circuits, and Paul Gray was the chairman of E department, Berkeley, UC Berkeley, also then the president of Berkeley. He's still there, of course, he's old, 81 years. So his book is one of the best analytical book as far as the feedback theory goes. Okay. So those who are interested to know more about feedback, please carefully look into this. The only problem is they are more from the old era, so they are much more bipolar circuits, though they added now MOS in last 10 years, 5-8 years, but still their emphasis looks to be more on bipolars. So I think that's the only reason why it's not so very popular. My course itself says CMOS, so I cannot say bipolar. So then there is a book by Ismail Esfez, it's not available in the market. The reason is that it's an old book. In India hardly anyone knows about it, okay. And I being the one know about it when I was in abroad, so I purchased one. And many of the interesting research in the area of analog, particularly low power or conveyor systems, I think came from Ismail and Vlsi people. He is still with Ohio University, so you can go on his site and figure it out. And of course some journals and some conference papers. There are other books are appearing in the market. Please, if you have some book which is good, maybe you bring to my notice. I will also look at it. But course doesn't require, because what I cannot change amplifier whether two books whatever they say, amplifier will remain the way it is, okay. So don't worry, if you have one of them is okay. Okay, so basic analog design with CMOS and analog system. We'll also see something about low power, low voltage. What is layout issue? Conclusion. This is only some overview. So wireless is the major driver for us. All VLSI designers are actually indebted to people like you who use mobiles, maybe two mobiles, these days iPad, iPod, whatever you talk, and all the WiMAX, Wi-Fi, whatever other hardware you create, this is the way money is available. And that's why most of the chips or most of the companies, except Intel, for no good reason, they fixed themselves to microprocessors, and I think another 30 or 50 years they may not leave that. But all other companies have some way or the other has shifted to wireless products. Qualcomm is number 1, Broadcom is number 2, and lines of them. Even TI, which was more signal processing, have finally entered wireless world last 10 years. Okay. So everyone is looking into wireless. Okay. So that is the major requirement. Then there are systems which are specific, optical systems. People are now looking into changes from electrical signal to optical. It's not new, it's quite some time, but more results are now coming. So there are many systems which are optical systems which may require our effort at least to interface them. Okay. There is a effort going on semiconductor 100% optical signal system. So there is no conversions, no losses. Okay. But the material they are using is semiconductor, mostly 3-5 materials, and partly silicon, but everything on semiconductor. So a link has been created which is 100% semiconductor based optical system and no transductions. The other area right now is sensors, and if you connect it to wireless, then that new word wireless sensor networks, as if it is great. Sensors were known, networks were known, wireless was known. You combine, you are in the world top 10. Okay. That's what this. So right now people are working, but sensors can be of any kind. Any energy to any energy is a sensing. You have to sense. There is also a catch between what is the word transducer and what is the word sensor. There is a lot of fight goes on. Basically sensor should only sense, that's the word is. But most people believe sensors means a transducer with a conditioning circuitry or what is called amplifier signal, everything on chip or everything together is a sensor. Okay. This is the way they think, I am not saying correct or right. Okay. So there are many systems which are requiring sensors now based connection to circuits. So these are markets. Then of course Intel's high speed microprocessor, 4 gigahertz, if you give, you say you need 6, you need 6, you say 10, why? Because that video game I want to kill that person faster, okay, somehow. So that microprocessor speed somehow is the marker for everyone how fast. Okay. So the huge effort is on high speeds. And of course to match them, then you need data transfers as fast as processor is asking. You need to look for high speed memories. Okay. So what is the difference between digital design and analog design? In digital design, if you are, I think you have done some digital circuit, but the other course is running 671 Vlsi design. So there we keep saying that look, digital design is basically hierarchical. That means I can have system break into smaller, and once I design break into smallest part, I design back up, bottom up. So AND gate can convert to XOR, XOR can convert to large, and we can go to any system. So the idea in the digital system, once designed, you can you don't have to redesign it, because AND gate doesn't change very much except for its driving, that is current how much it needs or drive it up. So these are more, what you say semi-custom, available, you can reuse it, but analog there is no such things. Every system you ask, you have to design it. So it's called custom design. Something, every customer requirement has to be met. Therefore analog designs in general are custom design, and in general people are now trying to make equivalent effort, like can we make VHDL instead of the AHDL, analog high speed hardware description language, can we do similar silicon compilers for analog. So there is an effort going on to do replication of digital into analog, but as of now most of the circuits are actually designed transistor wise, component wise. That's the strength as well as the weakness. Strength in the sense, for a teacher that's the best thing, because now he sees transistor. In digital you don't see transistor. A code लिख दिया हो गया, comparator हो गया, AND हो गया, XOR हो गया, इधर तो transistor दिखे. So something you can see what's happening is analog. Okay, and therefore you can design, oh, if I change size, if I change mobility, I change VT, what will happen? Is my GM is higher? So I am looking one to one what specs I am looking for. That digital doesn't require, because digital of course is the easiest designs. Okay, so the point is that it's a custom design, and therefore very interesting, because every design is required some way your so-called man satisfies his ego. If he say, yeah, I understood it, whether he understood is another issue, but he feels very comfortable that yeah, I have understood. That's why all these quasars, pulsars, the recent CERN experiment, what's great going on? If that graviton is not existing, you mean world would not have been, the world is still there. Now we are worried, is that kind of Higgs boson is available? That makes fun for us, okay? Because then it says, oh, so statistics is something like this, it follows, but it is like that, but it has a mass, so it is not like a fermion. So this satisfaction that we understood is always with us, and I wish IITians do not leave this part in their careers or in IIT. Okay. Do not become robots, remain humans. If you don't know few things is okay, but what you know you should know better. Okay. What you do is irrelevant, but how do you do is, okay. So what subjects you do in life, what you do is very irrelevant. Otherwise all kinds of people would not have been there successful. But how do you do matters. So work for the best of yours in whatever you do. That's what is important. That's human. Okay. And if you falter, more to learn. In analog circuit, power and speed, like in digital, is also important. The word in the speed in analog is converted to word bandwidth, okay, which is essentially in digital we call speeds. So few questions are always asked, why analog? So in 1980, many of the digital system designers, they started saying analog is dead, that's it, end of it. But 2000, you see more and more papers, more and more industries are entering analog. Okay. So something has changed or something necessitated that analog design be relooked into. Okay. The reason probably is we are now trying to see harness more of natural resources or natural systems, we are trying to play with them, and nature essentially is everything in analog. That is why the question came whether Big Bang theory is okay or solid steady state theory is okay, because nature doesn't like bumps, okay. It always goes one after the other. Darwin's theory, okay. That's how we became humans from all the other races. So nature is analog, so even if you process every signal digitally at the end, which is better in many cases, the front end will be always analog, because signals will be analog. So analog is a necessity, because any DSP ahead will require digital data which it can receive converted from analog signal. So that is one reason. Here is an example. I have an ADC and I have some input analog. If I convert it through ADC, maybe I will get the same truth table for it or bit data something like this, which may be fed to DSP. The problem is that the signal here, the strength of a signal or amplitude, when you convert through ADC, and if you have done ADC sometime, you know there is something called INL, DNL. Okay. So how much error it will create, because if it does not cross a threshold, it will not go to the next stage, next state. Okay. So it may remain in 0, it may not show you 1 where it was. So it should cross. So it is very unlikely that every time you will get a correct conversions. Okay, because analog natural signal may not be known to you and has actually known amplitudes. So the best way is therefore amplify it. It's an analog signal, amplify. Once you have amplified the signal, now you are almost sure what are the levels, and if you now convert it, and maybe other components, some frequency components, you can cut off from there other than the desired signal, you put a filter, pass through ADC, and you get a digital data. You are guaranteeing efficient way of converting an analog to digital. So that is why you need an amplifier, you need a filter before any DSP or ADC can be applied. So that is why analog cannot be just brushed aside. There are natural signals require digitization, will require at least amplifier, filter and an ADC. Now further going ahead, there are sensors of all kinds, mechanical MEMS, which is very popular these days in our group, optical, thermal, and they all energies are transduced into electrical signals, because we are electrical people. Anyone can convert mechanical to optical and get away, but we will not probably there, because we will like to see something signal microvolt, nanovolt or some volts or some currents. Okay. However, most of the outputs of sensors when converted or otherwise without amplifiers will be very weak and therefore has huge percentage of noise on that. Okay. So obviously the noise part has to be removed, so all the analog system which we create must be low noise, because otherwise they will pick up noise and add noise to it. Okay. And therefore the analog signal people must worry much more on the noise than what digital people work at. Now it is also not correct, but this is what I say, this is my statement. Digital data normally gets, if you transmit very long, unless you have a repeaters, it gets distortion or called distractions. Okay. So it is better if you have a transceivers of analog kind, because they will be faithful to your signals. Okay, always. How much additional hardware you require and how much money you may have to pay may be another issue. But analog transmissions will be, take a cable home, television. You have a very good signal coming, you see a beautiful videos. Okay. You actually connect a normal computer and put a TV in this, you see, it gives a good figure, but it has a huge lines in between. It's digital, because the pixel to pixel it picks up. Okay. Now this is essentially, one says that analog signal processing is far better than digital signal. If you see a hard drive disk, many times over the time, because they are magnetic in many cases, the signal becomes very weak, data is very weak. So it becomes very difficult to know ones and zeros there, and therefore what you read may not be what you wrote. Okay. So you need some amplification a priori before you read it out. Okay. Wireless, for example, the antenna which your mobile has, a very small antenna which has very little directivity. That means it has very small antenna gains. So the signal you receive is very weak. So the first thing you have to do is amplify, because otherwise that signal is less than few microvolts. Okay. So your circuit cannot actually behave also. So you need an amplifier right there after antenna. So I am trying to convince you that why analog. Okay. Microprocessor memories with ultra high speeds use clocks and signals, gigahertz, you are saying 4 gigahertz. As system clocks for Intel new processors may be 6 gigahertz. Now these kind of signals at such a high frequencies do not remain pulses. Okay. They actually get mashed up and they look more like an analog. What is the difference? Word analog means continuously time varying signals are called analog. Step signals are called digital, 0, 1 or maybe multi-value if you wish. Whereas in analog, amplitude keeps varying or frequency keeps varying with time, okay, that is a continuous. So your clock, if you see now, it is more like a continuous kind of this, there is no fixed wave, it is something like this, waves. So as much you may like, you are still doing analog signal processing even in the high frequency domain. The interconnects, which is the major worry right now on any single chip right now, okay, there are huge RC or RLC parasitics now, transmission line effects are very, very strong. And if you have done your theory of EM waves, which I wish you have, you will realize that transmission line theory creates, the impedance match, the reflections, VSWR, words which we use in there, they do now come into picture in our own circuits now, okay. And these are basically analog signal processing, okay. So what we are saying, even in the high frequency digital domain, you are doing analog signal processing anyway now. If you have a memory, I hope you have done some course, in particularly SRAM or DRAM, you say there is a, or any memory for them, there is a sense amplifier. The idea of sense amplifier is you do not have to see full voltage swing before output is given to you. So it senses 1 or 0 faster. So when you sense it, it has some kind of a diffam going there, which is an analog device, okay. So you look at systematically any digital hardware even now, you will find one way or the other you are directly or indirectly using analog processing. So learning analog is not very bad, worthwhile, okay. At least Qualcomm, Broadcom लोग तो आपको जॉब अच्छे देंगे. For example, you have a cable and you are inputting a signal V in and expecting an output V out. It is a good V in signal, good pulse is going, but what you see at the output, if the cable is lossy, which it will be most cases, there is nothing called lossless cable. Low loss cables is possible, but there is nothing called lossless cable. So even if you are lossy, the output you are going to get is not digital. You can see what signal you are actually transmitting. So essentially anything now you do at high frequencies in particular, you are actually worried more of analog problems than digital. आप कहेंगे सर इतना क्यों convince कर रहे हो? नहीं, ऐसा एक theory है कि you must know in mind that is this course really relevant other than the job, okay, which of course is, I maintain. Okay. So the question finally can come, why analog question for me is analog design more difficult than digital design? If you are asking me when I teach analog course, answer is yes. The reason is obvious. In a digital design, if you mostly it is inverter based or NAND or gate based, if you see the voltage levels which are allowed in digital, so let us say VDD and 0 are the uppermost and lowermost signal levels, up to VT 0 can go, and even up to half of VDD upper voltage can go, still it will be recognized as 1 and 0s, is that correct? So there is a huge noise margin available, so signal is not reaching peaks or not going to 0, does not matter, 1 0 are still recognizable. Okay. Of course there are 4 corners, high speed CMOS, in case of CMOS you may P slow, high, N slow, P fast, high fast and other 4. As that margin is too big, if you fit inside that 4 corner, you are safe, everything will work. Essentially related to sizing as well as temperature. So if you do that process and this together, if you fit within that, enough margin is available to you. Ideally switch has VDD by 2 margin, anything less than 1 and anything greater is 0. So it is a fantastic system, so you are not worried too much. Of course there is a trade-off still goes on there, their major worry is power connected with speed. Larger the power, larger will be, it will be high speed. This is very obvious, trivial in some case, because in most circuits the current which you are using is to charge the capacitor. Larger the current, C dV by dt is larger, time will be smaller, as straight as that. Okay. So faster means push current, okay. Higher current means higher power. Okay. So it is very simple that power cannot be low as well as speed can be high, but that is what digital people want, and that is what we keep doing, that how to beat the system. Low power, high speed, how do you do it? That is the game. Okay. So how to fool a circuit to do that? Externally you feel that I have achieved it, internally things cannot be changed, okay. But externally you still feel, oh, I have achieved low power and relatively high speed, okay, the games. Of course you can have third parameter there, area of the chip or area of the circuit, which can barter with that and can adjust to one of them. Whereas in analog it is not just bandwidth power, okay. It is power, frequency, gain, precision, which we call drifts, supply voltage, all of them actually affect the outputs, okay. So now when I am designing something, if I catch one, the other may go haywire. If I catch 2 or 3, the other 3 may not be within my hand, okay. And therefore design of an analog system really requires thinking, okay. That is why I said that word thinking more essentially means, yeah, some people like thinking, so for them analog design is simpler because that is what they want. But in general people want to bypass thinking, then digitals are the best, analogs are not. There are more problems with analog as well. Analog circuits are extremely sensitive to noise and crosstalks. Crosstalk, I suppose you little bit of aware, if two lines are going together, the signal on one line can interact with signal on the other, okay. That is called crosstalk. The worst crosstalk occur if the signals are moving opposite direction. If they are in same direction, lesser crosstalk. If they are in opposite direction, it is x minus minus y, so x plus y kind of situation. So crosstalk is major worry in most of the circuits now, digital included, or rather digital is worse right now. Because you are putting too much of interconnect there, too many lines going on, particularly like DSP, it has a lesser circuit, more interconnects. So now at such circuits you will find the problems are only on the crosstalks. So how to get rid of them? One method, of course, they suggest that put a ground line every between two signal lines, area, so paid price, which we do even now. The noise, any line picks up, like you put a wire, it picks up some voltage, essentially is noise voltage, thermal if nothing else. Analog, that noise is, there is no margin there, so any noise is also a signal. So if that goes, it also gets amplified, or whatever modification you do, noise also will get modified, okay. Nothing can be done. In digital device, second order effects, of course now they are also important in lower technologies, but earlier we used to say that. They will not so much important because of huge noise margins available in the case of digital. Analog, any variation, threshold goes by less than 0.1 volt. Current will be proportionally increased by that much, square law. Okay. Now this means, now suddenly you figure out small change, there we did not carry, here that has immediately GM has changed, bandwidth changed. Sometimes it will not within what you want, so the next stage may not work, okay. So there are issues which only analog has to tackle. So automation becomes therefore difficult. I am not saying it is impossible, but difficult, because every case has to be handled. Even in layouts, which are generally done by layout editors, final before mask is made, most digital people just go through a layout editors and generate patterns very fast. Analog, even if you do once, you will have to make 100-time intervention to, oh, this may not work better, okay, try this now, okay, resimulate again with a new one extracted. So there is game in analog layouts also, huge problems in analog layouts. We shall show you this part later. Then the models which are good for digital are no good for analog, okay. We will show you some of them. For example, there is a saturation parameter called lambda, we will show you in the current device. In the op-amp design case, the change in lambda is lambda to the power 4 in this change. So what you thought 5000 gain, you may get 5 or you may get 548 either, okay, depends on which way lambda moves. Lambda change the R zeros, and if you make products, it will go to the lambda to the power 4. In digital, nothing called such lambda, we actually leave lambda. Here that lambda cannot be left. So analog designer, therefore in my opinion, is a very smart guy who uses his experience and to a great extent intuition. This is what humans are. We have intuition, that is why we differ from animals. If we have no intuitions, we will be as bad. Okay. So when you use even the simulators, you have to have great experience, back knowledge and intuitions to design the newer system. So that is the difference between analog and digital. Now what is major worry for analog designers is this. Analog, independent analog chips are very few demand. Op-amps are made and they are sold. Only instrumentation people buy them. Very few such other systems buy op-amps per se independently. So I cannot have best of op-amp design like 8576, very low noise op-amp I can design. I can sell that also as on a board on a single chip on that. But a total mixed signal system, 80% of the part on that chip is digital or maybe more at times. So who will decide the technology? The digital people. The digital technology, which we call smaller channel length technologies, nanometers, 11, you want to go 0 nanometer MOS transistors now. So you want to reduce, but surprisingly when we do analog design, we figure out that larger the length better for us. Now here is the first conflict comes. Okay. I want to work on 0.35 microns, they say work on 16 nanometers. Now here is an issue. Okay. So the technology will be 16 nanometers and now I am told design your analog as good as what I am asking on this technology, which is not good for you. Okay. So that is the biggest challenge analog people face. If you are left alone, maybe I will use bipolars, which are the best analog components. Okay. But I will not be asked to do that. I say okay, आपका इतना एरिया है इसको बेस्ट बनाओ, सब इतना हमको गवर्न करोगे, how do we do? That's our major worry. CMOS of course is the best bet for digital circuit, and then whatever we do, analog has to be used, now has to be designed only on CMOS. It's not that I cannot design on any other technology or better or worse, by CMOS maybe even better. But because 99% digital circuit, mixed signal circuits are digital based, I'll have to work on all the time on CMOS because they work on CMOS. Okay. So there are issues which certainly are cropping up, not because analog is weak or something, you are given a bad tool and asked to design a very good system. Okay. That is where, but that's the interesting part because it's not easy, it's not easily thinkable. So your best comes out, okay, I can beat the system. Okay. At least I reach what he is asking. So finally in the end, analog IC design is successful implementation of analog circuits and systems using ICs. Their unique features are geometry is an important part of the design. This is most important, which is nothing in digital, but in analog, the geometry, the layout is the most crucial part of the design. Even sizing is very, very crucial. You create electrical design, from there you go to physical design, and from there finally when the chip is made, you test you have to create test vectors, so you have to test so all the three parts as in digital you will also have to do in the case of analog. As I said, they have to be implemented mostly for mixed signals, and as I said 20% analog, 80% digital on a chip. So 80% majority आजकल तो है, majority governs, democracy है. Because of that, analog circuits have to be, or analog design has to be on a transistor or a circuit level, more importance has to be given. Okay. There is a pass, means after I design and I fab and I test, okay. Then I see what specs I wanted and what did I get. This is called one pass. Most digital circuit because of the experience and expertise available now across the world, in one pass most circuit will come out. At best two in worst designers, if you are not a good designer. That means who are not good digital designer, that's what you should avoid in my class, but that's what the industry feels good. Who can copy best is the best digital designer. किसी और का design मार सकते हो, nothing better. Okay. It has worked, it worked for you also. Okay. Whereas in the case of analog, it may require 2 passes, it may require even 3 passes. So cost is very high for that. Okay. So that's why I keep saying analog. So what are the systems in mixed signal or analog we have? In analog system which we have are amplifiers, filters, comparators, oscillators or frequency synthesizers, the new name, multipliers, PLLs, phase lock loops, voltage current references, sample and hold circuits, A to D and D to A converters, high speed IO interface. This is another area where much of the work going on is high speed IO and DC to DC converter. Now this word is very interesting. This has been asked by me across IIT faculty interviews for assistant professor. Due regards to them who didn't answer. If I have a 5 volts volt supply and I want 2 volt or 1 volt, put a pot, we have done in second year lab, एक resistor लगाओ, divide करो, 2 volt मिले. So ये DC to DC क्यों करते हैं? DC से AC जाओ, AC से DC काय को? और तो वहाँ भी कंज्यूम हो ही रही है. नहीं कुछ और भी. You are not wrong. This is one important parameter. So DC to DC converter, and it is becoming very important even for digital now, because on a digital hardware now there is a what we call power supply unit or power management unit, which essentially create variety of voltages for variety of blocks of the digital part. Okay. So there, that's the analog part. Okay. That's why I keep saying analog is secondary लगता है, but उसको हटाओगे तो zero हो सकता है. Okay. We want to have analog design automation. Some of you can think over it. We can have automated layouts. We can have better simulation techniques than Synopsys or Cadence giving you for analog. Okay. We want to create hardware description language similar to digital if possible. And the best of course is you design and keep record of that, which is called intellectual property. Probably you can reuse it. You can sell IPs itself. Don't make chips, design an IP, fab test and say okay this is doable. So a op-amp from Atmel, you can actually buy an IP for an op-amp. You don't have to design. You find out from the specs which Atmel number matches required. Okay. You just ask, pay hell of money for getting that, but the effort of design is zero. Okay. Pay for it. Someone else has done it, use it. So there is another way of doing analog designs. Most Indian and abroad companies actually work on IPs. Either they create IPs or use IPs. Okay. So those who create IPs, IITians should join them because there is where the effort is, interesting effort is. If you look at the signal and information processing application for analog, almost every telecommunication, multimedia, automotive electronics, biomedical electronics, consumer electronics, neural networks, sensors, sensor networks, space and military applications or electronics. And of course, in all digital and digital signal processing itself now you will require analog. Okay, study. There are 2 kinds of mixed signal which probably many of you are not aware. Most of the teachers here are including me. Mixed signal means mostly digital, part analog. But there are other kinds of circuits available which are useful also, particularly for newer applications of bio, which are neural based. Okay. There most of the core is analog and some inputs or outputs are digital. Okay. So these are also mixed signals. Here analog is a major component. Okay. So neural processors is one example. We will show you the figure, and we will also show you some comparison of analog to digital. This is a typical neural processor. Okay. You can see from here, this is your computer or say data from where you can create digital data. You can have a DSP, some kind of neural DSP processing, convert to analog, then most of the processing is in neural analog, then again convert to A to D for feedback to digital, so that the system is stable as well as to switch. So if you see it, a digital part has vector quantizer, some codebook generators which come from PCs and through neural processors. Then there are a host of interfacing required, timing control. Digital requires, so is analog requires. Okay. If you see the analog part particularly, it is neural processor requires some kind of vector quantizer again, and it consists of synapses and matrix. If you have done a course on neural networks, you know about it. Maybe I'll show you as well. You may require summing of currents for neurons. You may require sample holds, and you requires encoders and WTA cells. Communication people know much about the word WTA. What is it? There is a famous song from 25 years ago, ABBA's song, first song, winner takes it all, WTA. Of course in bio it has another word, but in case of this, winner takes it all, WTA. So it's a majority circuit which takes winner. Okay. So these are the part of a neural processor which requires more analog processing than digital processing. This is an old slide of 98, so it's not very valid. The point we were trying to make then, why it is 98? Can you guess this word 98? In 1998, this course was written by me and first time taught in IIT, or rather any IIT. Everyone copied and kept saying we have started. Fair enough, all teachers do the same. We also took someone from Stanford or MIT and then we say we have done it. Other IITs doing, for me saying is equally good. Okay, at least they have seen my course is good enough. Okay. So this was the time when, so this was the old slide, so I just wanted to show you. Okay. So from this you don't have to go. The idea is to show here is that everyone believes that the analog processing is costlier. It's not true. If you look at the million connections updates per second or instruction calculation per second, analog is better than digital. Okay. So to some extent this idea should get out that digital systems are far superior to analog systems. Okay. This is only my word for you, because people have started believing that that is why digital is popular. No, digital is simple, cheaper, that's true. But otherwise if you have larger processing, even this can match you as much. Okay. But with larger analog there are more problems, so it's not catching up. But as far as theory goes, analog signal processing will be far better any day. You see the numbers, human brains require 210 to the power 9 million connection updates per second. We are still analog, at least we are reaching 20,000, digital 4-5. So we are no way reaching to the nature. Analog, at least we are coming closer to the nature. Okay. To some extent analog is still very much relevant for funda people. This is taken from Ismail Faiz. This is just to give you, I want to make a similar logic design kind of thing for op-amp. This is my aim. No one has done it, no one has succeeded. You have a mixed signal concept. This is called top-down design, bottom-up implementation, as we do in digital. You want to see, can we do in analog? So this is the flow. From concept, you can create architecture. Each architecture can be created to circuit blocks. Each should have some evaluation blocks, feedback to each, and from there to circuit, and maybe re-evaluate and feedback to mixing. The flow which we follow in digital, can we follow similar way in analog is ultimate for us. Okay. We are not, right now we do haphazard way. We design and say it's okay. So if you look at the analog, here is a typical digital inverter on your left, P channel device, N channel CMOS inverter. Depending on the input, low or high, P or N will be on or off, correspondingly output will be 1 or 0. Okay. So very trivial inverter circuit which is digital. The V out may not be as VDD, V out high may not be VDD, V out low may not be 0, but possibly we want to make it, and CMOS it comes very close to 1 and 0 as they are. Whereas if you look at analog, the basic circuit is an amplifier. Okay. Actually this is also an amplifier, there is no difference. I will show you what is the difference. This is an amplifier which has a resistor, which can be a transistor as well, and you have an N-channel driver. Please remember the word driver is used by us, which actually puts the input, receives input and puts the output. So it drives. In this case, one cannot say N channel is a driver because other signal is also connected to P, whereas in this case, this transistor is a driver. In NMOS inverter, yes, there will be a driver transistor and a load as it is. This is like an NMOS inverter as well. So what is the fun part in this is this: if I plot for an inverter or an amplifier V out versus V in, you have done this in many courses. Okay. This is normally VDD, this is normally VDD. There are of course, as I say, 5 regions, but at least 3 shown here. Anything V in less than somewhere here, V out remains high. Anything beyond, maybe sorry, VDD is here, not here, somewhere. Anything beyond certain value of V in, the V in becomes VDD, this becomes 0. This is what normal inverter shows. And we normally don't worry about this part. The reason is we are only worried about these levels in digital, 1 or 0. So input goes 1, output should go 0. Input goes 0, output should go high. It transits, we don't care too much. We do, but not so much. If you see the gain here, dV0 by dV in is how much? 0. Same way here. So this is 0 in these 2 regions. But what is here? dV0 by dV in, which is gain, which is negative value, is my gain. So if you are looking for an amplifier, obviously you cannot operate on this region and this region. You can only operate in very small region. And if you use a CMOS, you can see this will be even sharper like this. This is very interesting. That means dV0 by dV in is very high in transitions. So analog circuit only work in this small input range. That's why small signals. Where digital can go from 0 to VDD. Okay. So gain part only comes in a very small inputs. Okay. So we are worried all the time about this region in the case of analog. Is that clear to you? So the transistor must remain biased in this region to keep amplification. In digital you don't bias because you are not interested in gains anyway. Of course it does have influence on speed, margins. I am not trying to say digital does not get affected by that. In fact, depends on size, it may shift and it may reduce the margins as well. But typically digital we damn care because we are only interested in the 2 ends. Okay. Analog we are only interested in between, okay, which is the gain function. So one has to accept that the first difference between the 2 circuit is the input range. Otherwise this can be used as an inverter, okay, this whole as can be used as an inverter. So as you can say this is an inverter because it allows you to shift VDD to ground, whereas this input is limited and the bias which is not shown here is exactly in that range in which gain is possible. Is that clear? Exactly, that's the reason why analog is interesting. If you see comparisons, the digital circuits are highly non-linear. You have just seen the characteristics, very non-linear. Linear means dV0 by dV in, except at the edges it is constant. Okay, so linear. Okay, another second year student who have passed, y is equal to mx plus 3c is linear, but it is not a linear system. Okay, so do not confuse between linearity and systems. Okay, so it's a highly non-linear, high noise immunity. immune to power supply variation, because as I say margin is high, VDD upar 5%, who cares, and 1 bit at a time is the information transfers, so no worries. If you look at the analog, it's very linear, that's the gain is required, extremely sensitive to noise. Now you can see anything now on this will also get amplified. So any small signal also has a larger gain seen by it. So now apart from signal, any noise also will come to you, okay. Whereas in the case of digital, damn care, okay. So it's very sensitive to noise and therefore worry. Any power supply variation is also worrying because it will directly reduce the currents and therefore GMs and everything, and carries more than 1 bit of information, okay, and therefore it's multi-bit transmission. There are issues right now which I worked many years ago, and again at the what is the solar cell center people are now looking into for solar cell as well as electronics. There is a problem of natural radiation falling on the circuit, okay, and particularly if you are a satellite based circuits, intense radiation is there. So if you see the two comparison for radiation purpose, there is a huge threshold shifts, there is a mobility degradation, and therefore speed varies, changes much more. There can be huge power consumption change, okay, before and after irradiation, and there is what we call single event upset due to alpha particle hits. Okay. If you look at analog, now this spelling, analog GUE, this is British. Okay, so analog functions are affected by, here only small amount, here everything is affected. So if you have an analog block, any op-amp circuit sitting on your satellite, it will fail faster, that's our worry. It changes operating point, changes bandwidth, changes gain, change offsets, change stability, whatnot. Okay. Then it also control over biasing voltages or current when possible, allows some compensation of radiation effects. You can actually play with band gap references and feedback paths to compensate some, which is not possible in the digital. So some advantage, some disadvantage. SU is certainly not important issue. Okay, this figure is not clear, we will come back to it later. So basically what is analog circuit design needs to consider. In case of analog, positive and negative signals both are required, because generally it is a VDD minus VDD, dual rails. Biasing is very important, just now I showed within the gain range only you can keep the device. So if you shift out, there is no gain for you. Linearity is essential, gain has to be constant. So you are looking for, that's why they are called linear circuits, because they are constant gains. We want in general any circuit, but analog more, less prone to noise, because otherwise noise will supersede everything. We want smaller change in parameters, it's called drifts. The problem, as I say, is there are no standard sets available, blocks available we can use, so we may have to either create our own and reuse it or design every time. Then very difficult right now is to design low voltage circuits and therefore low power circuits or maybe low energy circuits. There are 3 parameters which you shall work in analog design. These are our, what you should say, bread butter parameters. The transconductance GM, output resistance R0, and the third and the most important, input referred noise. That's the 3 parameters important as far as the gain side is concerned, outputs are concerned. And finally, for all analog circuit, we are worried about bandwidths, okay, which is our frequency response. So how do you tackle each of them and still do not lose on others is what the game is all about, designs. Okay, so we stop here today, okay, we'll come back next time.